Welcome to our discussion on matrices and systems of equations. This is going to show us how we can use matrices to solve, well, any system of equations, but we normally use them for 3x3s and above because a 2x2 is so easy to do with the elimination or substitution method. It's often quicker and simpler just to do it with those methods rather than putting them into matrices. But once you get really good with matrices, you can do them faster with a matrix as well. As always, fast forward if you only need to review a certain topic. Here is a definition of a matrix. If you've never seen one before, it's basically just a collection of a bunch of numbers in what looks like some sort of weird little rectangular shape with these funny little brackets on the side of it. We describe matrices by how many rows and how many columns they have. Right? We start in the top left, and this is row 1 and column 1, row 2, column 2, and so on. We can designate each number in a matrix by where it is, what its location is by rows and columns. So you can see this second number here is A12 because it's row 1, column 2. So if a matrix has m many rows and n many columns, then it's said to be an m by n. So we always write matrices in row by columns. So a 3x4 matrix would have 3 rows and 4 columns. It's that simple. If something is in the 5th row and the 6th column, it's going to be A sub 5, 6, right? So the first number, the I, represents the row, and the J represents the column. If your matrix A has n rows and n columns, meaning they're the same number, then we call it a square matrix. So a 2x2, a 3x3, a 4x4, and so on and so forth. The entries along the main diagonal will have, 1, 1, 2, 2, 3, 3, 4, 4, all the way to however big it is. And those are important numbers to know, so that's why we kind of point those out. If A is a 1 by n matrix, it's called a row matrix because it just has one row, and then n is how many columns it has. And then if it has n number of rows and then a 1, so like a 5 by 1 or a 6 by 1 or a 2 by 1, that's called a column matrix because it's just one column, right? It's so many rows by one column. Okay, let's use our knowledge of what we just learned to make sure we understand the order of these matrices and then identify rows and columns and items and all that stuff. So our first one, hopefully you're looking at that and going, well, that's a 1 by 1. And it actually has a diagonal, right? A11 is 3. Okay, B, that's a 1 by 3. And that's what we would call a row matrix. And because it's not square, it doesn't have any things on the diagonal, but this is still item 1, 1, 1, 2, and 1, 3. Okay, 2 by 2, it's square, so we can look at the diagonals. There's 1, 1, there's 2, 2. 3 by 3, so it has a diagonal, 1, 1, 2, 2, 3, 3. All right, let's actually use a matrix to solve a system. So if we were given this 3 by 3 linear system of equations, we can write it as a matrix, and basically all you're doing is writing down all the numbers without the variables. So you just write down the coefficients. So there's my 1, minus 1, minus 1, and 1, right? And so on and so forth. We put a little vertical line here to represent that these are the constants that were on the other side of the equal signs. And then these are all the coefficients of our variables. And that's important to do. So you can see why it was very important that when we were learning how to solve these systems that we always line them up with the variables corresponding in columns, because now this is the column of x coefficients, this is the column of y coefficients, this is the column of z coefficients, and this of course is the column of constants on the other side of the equal sign. Okay, elementary row operations just means the things that we're allowed to do to our matrices that keeps the resulting matrix equivalent to the original matrix, which in essence just means if we mess around with these numbers, we're really messing around with these numbers. And so if you remember, what were the things we were allowed to do to a system of linear equations that were still equivalent? We were able to swap, right? We were able to trade places. We could take this equation and trade places, or these two, and so on and so forth. Well, That's what this says, interchange two rows, because that's just interchanging two equations. We also learned that we were able to multiply any of these equations by a non-zero constant, because if you multiply by zero, that's just stupid, because then you just get all zeros. Well, multiply a row by a non-zero constant. Same thing, right? And then the third thing that we learned we were able to do with these things is we were able to add non-zero multiples of rows together and let them be the new row. So like we could take this row, multiply it by, let's say, -3. Take this row, multiply it by, let's say, 5. Add those two together and let that be our new row 3, or we could have let it be our new row 2, right? It could always take the place of whichever equations, right? If we were using the second and third equation, then when we add them together, it has to take the place of either the second or the third equation. Well, we can add a multiple of one row to another, and that becomes the new row. So that's the same thing, right? So whatever we could do with equations, we're now doing with rows. All right, let's look at some examples of what that means. So this little symbol just means swap R1 and R2, right? Trade places with the rows. So we take these two, we trade places, and there they are. We call that the new matrix B, because it's no longer the same matrix. They're equivalent, but it's different. So here's our first one that we started with, right? Here's the new one where we swapped them out. Then the second thing we wanted to try was multiplying the first row by a half, what we got here. So now that's a new matrix, call it C. You don't have to keep calling it new names, by the way. We're just keeping track. Now it said we wanted to add -3 times the first row to the second row. So we take this new row 1, right, that we have, multiply it by -3, and add it to this. So -3 plus 3 gives me 0, right? This would be -6 plus -2 is -8, and then -21 plus -3, -24. So you can see that all we're doing with these matrix rows is the same stuff we were doing with our actual equations. We just no longer have to write all of the variables. We don't have to write x, y, and z each time. We just have to deal with the coefficients. So a matrix is just a time saver, right? It's like shorthand. Okay, what does it mean to be what's called row echelon and reduced row echelon? If you remember when we were dealing with our 3 by 3, we got things into triangular form. Well, triangular form is what we call row echelon form. And then once you back substituted in the previous and got what x, y, and z actually equaled, that's basically what happens when we have reduced row echelon form. So again, same things we learned before. All right, so what does it mean to be in row echelon form? Well, the leading entry of each non-zero row is 1. So the first non-zero number in each row has to be 1, and that's what it was with triangular. The leading entry in a row is to the right of the leading entry in the row above it. That just means that it looks like a triangle, right? So the top row has all 3 numbers, but then the second row had a 0, and then it only had 2 numbers, right? We got rid of the x, and then we just had y and z. And then the third row, we got rid of x and y, and we just had z, so we would just have 2 zeros and then a 1. So you see how kind of they get smaller and smaller. And then all non-zero rows are above rows consisting entirely of zeros. So that just means if you had any things where everything canceled out and you had all zeros, you always put that on the bottom of your matrix. Okay, if we want to be in reduced row echelon form, then in addition to all of those previous things, we also have to have each leading one is the only non-zero entry in its column. So basically we take that triangular form and we work backwards and we get rid of the extra stuff above it. It'll make more sense when we do an example. All right, so let's do an example. Let's use this Gaussian elimination to actually solve a system. So step 1 is we write the matrix, right? So we take our system of equations, we write it as a matrix. Then we use those elementary row operations, which are the same things we learned for, messing with the equations, to get into row echelon, not reduced row, but just row echelon. Once we have that, we put it back as a system of linear equations and then use back substitution to actually find the solutions. This is a stupid pain and waste of time doing this, right? We're going to do Gaussian elimination once just to show you how it parallels nicely with what we were doing before with the triangular method of working with systems equations. But to write this back as a system of linear equations and then do all that back substitution is a lot more effort than it is to just do what's called Gauss-Jordan elimination, which is basically just taking, instead of stopping here at row echelon, you go a little bit further and get your matrix into reduced row echelon form, and then all of the answers are just staring you in the face. Much easier. And you'll see when we do that example. Okay. Gaussian eliminations. Start with your system, write it as matrix, right? So you just write out all the coefficients. Don't forget your little line to designate these are the constants. That's step one. Okay, step two, we do all of our row swapping and multiplying and all that junk to get it into that triangular form, right? Where we're going to have ones along the diagonal, who cares up here in the upper stuff, and then zeros down here. So first things first, right, we swapped it out. So we had a 1 here, then we multiply by 3 and add to make this a 0, right, because 3 plus -3. Then we multiply the top one by -2 and add it to this one. You notice that we're always adding, right? You don't want to subtract, so you always want to multiply by negative if you have to in order to swap something out or eliminate something, sorry, because you always want to add. That's the safer of the two. Okay, so we got rid of our x's and we have zeros here. Now we're going to repeat the process down here, make this a 1, and then get rid of this stuff. So we multiply through by -1, then we can just simply add it to here to make that a 0. And now we have this. Last things we have to do is make that a 1, so we divide by 4. And here we are in what's called row echelon form, not reduced row echelon form. Reduced row echelon form would just be zeros up here, so we would have to get rid of these three numbers. And you can see that it'd be very easy. We could get rid of this 1 by just taking this and subtracting this one from it. Remember, we don't want to subtract, so think about multiplying by -1 and adding. And then this would be a 0. And then we'd have 0, 1, 0, and then something here. And then all we would have to do is, again, use this one to get rid of this by adding it. And then use this new one where this is just a 1 and a 0 to get rid of that one. And then we would have all zeros up here and we'd be good to go. But if we didn't, and instead we just stopped here, then now we rewrite it in terms of x's and y's and z's, and then do back substitution. Put the 3 in here, move it over, solve for y. Put the 3 and the y in here, move them over, solve for x, which is what we're doing here. Right, there's my y, there's my x. So here is my ordered triple, there's my solution. We'd want to plug that into all three and double check that it works. What happens if we try this same technique, right, this Gaussian elimination now, instead of doing it the way we learned with just the equations? How does this still work with no solutions and infinitely many solutions? So here's an example with no solution. So we put it in our matrix, we do our swaps, right, we do our eliminations, we get it down to row echelon form, but what happens is instead of having a 1 here, we get all zeros and a constant. Now, of course, they're going to show you technically you need to then divide by 8. And of course, 0 divided by 8 is still 0, and you get zeros with a 1. Basically, as soon as you get to this point, you know you're done. Because this is back to that idea of 0 equals something that's not 0, right? So 0 equals 8, which is false, right? It's not true. It's impossible. No solution. Right? They just made it 0 equals 1, but 0 equals 8 is the same thing. False statement, no solution. Okay, let's look at how we can do it with the Gauss-Jordan elimination method. So we start like we do normally. We take our system, we put it into a matrix, we do all those row operations to get it into row echelon form here, right? This kind of what's called sometimes upper triangular form, because you can see the upper triangle still has numbers, but the lower triangle is all zeros. Normally at this point, if we were doing the Gaussian, we would divide by 5, make this 1 and 3, and then we would rewrite it back in terms of x, y's, and z's and do reverse, back solving. But instead, we continue on. So here's row echelon form. Now we need to use this to get rid of these three numbers, right? To make these all zeros. So the first thing we can do is we can add row 2 to row 1 to get rid of this one, which is what we did here, right? Those go away. That becomes -4. That becomes -7. There's my new one, right? Then we can take this bottom one, multiply it by 4, and add it to this one, which is what we're doing here. and that gives us 5, right? Because 4, that one, and 4 times 3 is 12. 12 minus 7 is 5. So that's how we get that. And then to get rid of this negative 3, we have to multiply the bottom one by 3 and add it. Those will go away, and then this will be 9 minus 8 is 1, right? So that's where we got this. And now that we have all zeros everywhere but the diagonals, we're done. This says x, right? 1x plus no y's plus no z's equals 5, so x equals 5. No x's plus 1y plus no z's equals 1 means y equals 1. And then no x's plus no y's plus 1z equals 3 means z equals 3. And we get the same solution we got the other way. It's just, I think, a little cleaner and simpler and easier than putting it back into terms of x's, y's, and z's and doing all that back substitution stuff. Okay, so that's what's called the Gauss-Jordan elimination method. All you have to do is take those upper triangular numbers, those numbers up here, and turn them into zeros as well. And that's what it meant when we were going through the definition, that the leading coefficient of 1 is the only non-zero coefficient in every column. So you can see that here it's 1 with all zeros. Here's a 1 with zeros above and below, and then here's a 1 with zeros above it. So it's the only non-zero number in each column, because then, remember, this was the x column, the y column, and the z column, and now we know what x equals, what y equals, and what z equals. Okay, so here's an example with infinitely many solutions. Right? We know before with no solutions we got 0 equals a number. Now we're just going to get 0 equals 0. We put in our matrix, we do all of our manipulations, move stuff around, and all of a sudden we get a row of all zeros. It doesn't have to be the last row, guys. It can happen anywhere. As soon as you get a row of all zeros, you know that you're going to be in a bad way, right? Because the only way to get a solution to 3 equations is to have, or sorry, to 3 unknowns is to have 3 equations. And once we get all zeros, we've basically lost an equation. We now have just the remaining 2. But we still want to put it in reduced row echelon form. So we get it looking like this. We get rid of the 0 here, right? Because we still have this 1, so we can get rid of that one. But we can't get rid of this 3 because we don't have a number down here. So this is as reduced as we're going to get it. Once we have it in that spot, then we put it back into the equations, right? So x minus 3z equals negative 4, y plus 4z equals 4. That's where these come from. And z, remember, was just the arbitrary thing. That was the thing where z could be anything. So now we solve these things in terms of z, and we see that y equals this, x equals that, and then our full solution is z is just z, right? Y is the negative 4z plus 4, and x is the 3z minus 4, and we have infinitely many solutions written in terms of z. Okay, guys, that's how we use matrices to do the same thing we've been doing before. It just kind of speeds things up. It's a shorthand where we no longer have to write all of the letters. We can just do it with just the coefficients.